The universe is a vast and mysterious expanse filled with phenomena that challenge our understanding of space, time, and the very nature of reality. Among the most enigmatic of these phenomena are black holes, cosmic giants that consume everything in their path, including light itself. These celestial objects, born from the remnants of massive stars, possess gravitational forces so powerful that they distort the very fabric of space and time. With the advent of advanced technology, particularly the James Webb Space Telescope, JWST, scientists are beginning to uncover new insights into these mysterious entities, reshaping our understanding of the universe. Black holes are not just ordinary celestial objects. They are regions of space where gravity is so intense that nothing, not even light, can escape their grasp. This makes them incredibly difficult to observe directly. The most massive of these, known as supermassive black holes, are found at the centers of galaxies and can have masses ranging from millions to billions of times that of the Sun. Their origins and growth are subjects of intense study and debate among astronomers. These supermassive black holes are believed to have formed from the remnants of dying stars, but the exact process of their formation remains one of the greatest mysteries in astrophysics. When a massive star exhausts its nuclear fuel, it undergoes a catastrophic collapse under its own gravity, potentially forming a black hole if the mass is sufficient. The resulting black hole continues to grow by accreting matter from its surroundings, often forming an accretion disk of gas and dust that spirals into the black hole, heating up and emitting intense radiation in the process. The first ever image of a black hole, captured in 2019 by the Event Horizon Telescope, was a monumental achievement in the field of astronomy. This image provided the world with visual proof of the existence of black holes, specifically the supermassive black hole at the center of the galaxy M87, located about 55 million light-years from Earth. This groundbreaking image showed a bright ring of light surrounding a dark shadow, which is the event horizon, the point beyond which nothing can escape the gravitational pull of the black hole. This historic image was not just a visual triumph. It confirmed many predictions made by Einstein's theory of general relativity. The successful capture of this image required the coordination of a global network of radio telescopes, essentially creating an Earth-sized virtual telescope. This achievement has opened new avenues for studying black holes and has confirmed that these cosmic giants are not just theoretical constructs but real entities that play a crucial role in the evolution of galaxies. While the image of the black hole in M87 was a recent achievement, the quest to confirm the existence of black holes dates back much further. The first strong candidate for a black hole was Cygnus X-1, discovered in 1964. Cygnus X-1 is a stellar mass black hole, significantly smaller than supermassive black holes, but its discovery marked a turning point in the study of these objects. Located about 7,200 light-years from Earth in the constellation Cygnus, it is part of a binary system where it is paired with a massive blue supergiant star. The black hole's presence is inferred from the X-rays emitted as material from the companion star is pulled into the black hole's accretion disk. These X-rays, detected by early space-based observatories, provided the first strong evidence that black holes were not just theoretical objects but real observable phenomena. The discovery of Cygnus X-1 was met with excitement and skepticism in the scientific community. Stephen Hawking and Kip Thorne, two of the most prominent physicists studying black holes, made a famous bet in 1975 regarding whether Cygnus X-1 was indeed a black hole. Hawking, always the cautious scientist, bet that it was not a black hole, possibly to hedge his bets against the lack of definitive proof at the time. Thorne, however, was confident in the interpretation of the data. Over the years, as more observations accumulated, the evidence for Cygnus X-1 being a black hole became overwhelming, and in 1990, Hawking conceded the bet. The confirmation of Cygnus X-1 as a black hole was a significant milestone, providing a foundation for the study of black holes and their properties. It also highlighted the challenges scientists face in proving the existence of these elusive objects, which cannot be observed directly but only through their interactions with surrounding matter. Despite the theoretical predictions and indirect evidence, detecting and studying black holes remains an incredibly challenging task. Unlike stars, black holes do not emit light, making them invisible against the backdrop of space. Scientists rely on the effects black holes have on nearby objects to detect them. This includes observing the motion of stars and gas clouds that orbit these unseen objects, as well as detecting X-rays emitted by material as it is heated to extreme temperatures while being drawn into the black hole. One of the most significant challenges in black hole detection is the need for precise and sensitive instruments. The X-rays and other forms of radiation emitted by the accretion disks of black holes are often faint and can be easily drowned out by other sources of cosmic noise. Additionally, the vast distances to many black holes mean that the signals we receive are incredibly weak, requiring sophisticated equipment and techniques to detect and analyze them. The advent of space-based observatories such as the Chandra X-ray Observatory and the more recent James Webb Space Telescope has greatly enhanced our ability to detect and study black holes. These observatories are free from the distortions caused by Earth's atmosphere and can observe the universe in wavelengths of light that are blocked by the atmosphere, such as X-rays and infrared. This has allowed astronomers to study black holes in greater detail and has led to many new discoveries. The James Webb Space Telescope, JWST, launched in 2021, represents a new era in space exploration and the study of black holes. With its powerful infrared capabilities, the JWST is designed to peer into the distant universe, capturing light that has traveled billions of years to reach us. This makes it an ideal tool for studying the early universe and the formation of the first galaxies and black holes. One of the key advantages of the JWST is its ability to observe in the infrared spectrum. Infrared light can penetrate dust clouds that often obscure visible light, allowing the JWST to reveal structures and objects that would otherwise remain hidden. This is particularly important for studying the regions around black holes, which are often shrouded in thick clouds of gas and dust. The JWST has already made several groundbreaking discoveries in its short time in operation. Among these is the detection of a massive dormant black hole near our solar system, located within the Milky Way galaxy. This black hole, known as Gaia BH3, is the second closest known black hole to Earth and has a mass approximately 33 times that of the Sun. Despite its proximity, Gaia BH3 remained undetected until the JWST and other observatories provided the necessary data to confirm its existence. Gaia BH3 is located in the constellation Ayla, about 1,926 light-years from Earth. It was discovered by accident as scientists analyzed data from a European Space Agency's Gaia mission, which is mapping the positions and motions of stars in the Milky Way. The discovery of Gaia BH3 highlights the capabilities of modern telescopes and the surprises that still await us in our own cosmic backyard. Gaia BH3 is classified as a dormant black hole, meaning it is not actively accreting material from a companion star and therefore does not emit significant amounts of radiation. This makes dormant black holes particularly difficult to detect, as they do not produce the bright X-ray emissions typically associated with active black holes. Instead, their presence is inferred from the gravitational effects they have on nearby stars and other objects. The discovery of Gaia BH3 is significant because it provides astronomers with a rare opportunity to study a black hole that is not currently active. By studying the motions of the stars orbiting this black hole, scientists can gain insights into its mass, spin, and other properties. This, in turn, can help us understand the life cycles of black holes and the factors that determine whether they are active or dormant. Dormant black holes like Gaia BH3 are thought to be relatively common in the universe, but they are challenging to find. The discovery of Gaia BH3 so close to Earth suggests that there may be many more dormant black holes lurking in our galaxy, waiting to be discovered. As our observational techniques continue to improve, we may begin to uncover more of these hidden giants. One of the most exciting aspects of the JWST mission is its ability to study the early universe and the formation of the first black holes. The early universe, just a few 100 million years after the Big Bang, was a time of intense activity with the first stars and galaxies forming from clouds of gas and dust. It is during this period that the first black holes are believed to have formed, but the details of this process remain shrouded in mystery. Recent observations by the JWST have provided tantalizing glimpses into this distant epoch. One of the most significant discoveries is the detection of an extremely red supermassive black hole in the early universe, located about 12.9 billion light-years from Earth. This black hole, estimated to have a mass of around 40 million times that of the Sun, is among the earliest and most massive black holes discovered so far. The discovery of this red supermassive black hole challenges existing models of black hole formation and growth. The fact that such a massive black hole existed less than 1 billion years after the Big Bang suggests that black holes can grow much more quickly than previously thought. This raises questions about the processes that drive the rapid growth of black holes and how they interact with their host galaxies. The discovery of supermassive black holes in the early universe also brings to the forefront a fundamental question in astrophysics. Did black holes form first, or did galaxies form first? This is often referred to as the chicken or egg dilemma in the context of cosmic evolution. The exploration of black holes not only enhances our understanding of cosmic phenomena, but also drives the development of new technologies and methods. As astronomers push the boundaries of what we can observe, they are constantly developing more sensitive instruments and innovative techniques. These advancements help us explore the extreme conditions near black holes and gather more detailed data about their properties. One exciting area of research involves the study of gravitational waves, ripples in spacetime caused by massive objects like black holes merging. Detectors like LIGO and Virgo have already observed several black hole mergers, providing crucial information about their sizes, frequencies, and the nature of these cosmic events. The ability to detect and analyze gravitational waves offers a new way to study black holes and test theories of gravity. As observational technology continues to improve, future missions and telescopes will further refine our understanding of black holes. Upcoming projects, such as the next-generation space observatories, are expected to provide even deeper insights into the behavior of black holes and their interactions with their surroundings. These advances will likely reveal new aspects of black hole physics, including their role in galaxy formation, the nature of their interiors, and their ultimate fate. In summary, the study of black holes is a dynamic and rapidly evolving field that continues to captivate scientists and the public alike. Each new discovery pushes the limits of our knowledge and reveals more about these mysterious cosmic giants. As technology and research methods advance, we can expect to uncover even more about the ultimate nature of black holes and their impact on the universe. As we delve deeper into black hole research, scientists are also exploring the theoretical implications of these findings. The mysteries of black holes challenge our understanding of fundamental physics, particularly the reconciliation of general relativity with quantum mechanics. One significant area of interest is the information paradox, which questions whether information about matter that falls into a black hole is lost forever or if it can be recovered. This debate touches on the very fabric of reality and how information is preserved or destroyed in extreme conditions. Additionally, the study of black holes provides crucial insights into the nature of dark matter and dark energy. By observing how black holes influence their surroundings, researchers can infer the presence of these elusive components of the universe. This could help solve some of the most profound questions in cosmology about the composition and fate of the universe. Moreover, as our observational capabilities expand, black hole research might uncover new types of black holes, or even entirely new phenomena. For example, intermediate mass black holes, which are between stellar and supermassive in size, remain elusive but could offer new insights into the formation and evolution of black holes. Similarly, the potential discovery of primordial black holes, formed in the early universe, could shed light on the conditions of the early cosmos and the formation of the first galaxies. In essence, the ongoing exploration of black holes not only expands our knowledge of these cosmic giants, but also pushes the boundaries of our understanding of the universe as a whole. Each discovery leads to more questions and fuels the quest for answers, ensuring that the study of black holes remains one of the most exciting and transformative fields in modern science.